All right, welcome everybody. So in this video, I want to apply the least squares solution that we've derived to this motivating example that we've been discussing about trying to predict a country's wealth, their GDP per capita, if we knew their literacy rate and their life expectancy. So down below, we have our matrix A that we'll call a model matrix, and this corresponds to the observed literacy rates, which are in the column for A1, and the observed life expectancies, which are the second column of this matrix. So each row is a different observation, is a different country, and we have a pair of values, their literacy rate and their life expectancy. And then vector B is our vector of response values. The response here is the GDP per capita. So this is country 1, their GDP per capita, country 2, and country 3. And so we would like to find a model for this data. Well, we've chosen a linear model of the form AX, these are our betas, is equal to some predicted value that we denote B hat. And the solution here, the least squares solution, is going to be the vector that I pick for x, in other words, the betas that are going to make my predicted value as close to the observed values that we have. And we've derived the solution that is when we can find the inverse of the matrix A transpose times A, we have a unique solution that we denote x hat. So this is the least squares solution, which is equal to A transpose A inverse, all times A transpose times B, this vector of observed response values. So there's a link to a Google Colab notebook in the description of this video where all of the calculations on this slide are done. I don't want to get bogged down in the calculations, but I do want to make sure the process for how we use this equation that we have up top to find the solution makes sense. So we first will compute the matrix A transpose A just to make sure that this is invertible. And we're going to be fine because the only way this A transpose A is not invertible would be if these two columns of matrix A were linearly dependent. And I can see that column 2 is not a multiple of column 1. So these two columns are linearly independent, which tells me the matrix A transpose A should be invertible. So here's A transpose. Here's the matrix A that we organized our data into. And taking the product of these two matrices, I get this 2 by 2 matrix below, where the first column has first entry 24,629. The second entry in that first column is 20,424. In column 2 is 20,424 and 17,044. So the values, when we're working with observed data, typically are not necessarily going to be so nice. And that's why we often use technology when we're solving least squares problems. So now let me calculate the product A transpose B. So I found this piece over here, and next we're going to calculate A transpose times B. So A transpose, again, would just be this matrix over here. B is the matrix 13, 11, 8. So taking the product of these two matrices gives us this vector, which has first entry 2,901 and second entry 2,426. And again, you can verify these calculations with the Colab notebook. So now we're ready to find our solution x hat by taking the inverse of the product A transpose A and multiplying that by the product A transpose B. And that is all organized over here. So here was A transpose A. We're going to find the inverse of that matrix and then multiply that by A transpose B, which is over here. And so multiplying A transpose A inverse times A transpose B gives us a vector which is approximately equal to minus 0.039 and 0.190. And so what this tells us, great, we just solved this least squares problem, and this gives us a nice model. This tells us if I'm going to construct a model of the form wealth is equal to beta 1 times the literacy rate plus beta 2 times the life expectancy, then the coefficients that are going to work best are going to be beta 1 should be minus 0.039 and beta 2 should be 0.190. And now we can kind of look at this model and think, does it make sense? And if it doesn't make sense, then maybe we should pick a different model. And one thing that looks a little strange about this model is if the literacy rate of a country goes up and we don't change their life expectancy, this negative sign here is telling me that the wealth of that country is going down. And that's a little bit counterintuitive. You might expect that countries that are more educated might tend to also be a little bit wealthier. And the fact that I'm getting a negative value here, this has me believing not necessarily that I didn't find the best possible values for beta, but maybe a linear model is not the most appropriate model here. And we can talk about how we can tweak this to find a more appropriate model. But based on the choice that we made, that we wanted to find a model of the form beta 1 times literacy rate plus beta 2 times life expectancy, then this would give me the best model of that form.